All right, folks, this is going to be a video on confidence intervals. We're going to do a one prop confidence interval and a two prop confidence interval for proportions. Okay, for population proportions. That's what we are trying to estimate. So I have two questions off AP Stats exams. This one for one prop Z interval. This one for two prop Z interval. Okay, so just so we know again, all right, here are our formulas when we are dealing with either one population over here or two populations over here, right? Here is your standard error, right? Remember, we're going to end up having to use standard error because if we're trying to estimate the population proportion, we're not going to have, we're not going to have P. So we're going to replace it with our next best guess, which is going to be P hat, which is going to come from our sample. And so we can't call this a standard deviation anymore. We now have to call it the standard error of P hat instead of the standard deviation of P hat. And when you're dealing with samples from two populations, okay, so we're trying to estimate the difference between two proportions. All right, here's your formula. It's basically this formula right here, but we're going to add those, basically the variances together, right? We're adding them together before we take the square root, which doesn't make them standard errors. These are variances then. All right, so we're going to get the information from our first sample, right? One sample size from one population and the statistic that we get from that sample, plus here is my second population sample size and the statistic that we get from that sample. Add these two variances together, take the square root, and now you have your standard error. And then down here, this is specifically for when you're running the significance test and you have to pool. Remember, we talked about pooling, right? If we're going to assume that population 1 and population 2 are equal, we need to pool. So this is how you pool. And I don't know why they write the formula like this, right? We should take this piece here and distribute it into these parentheses. So you'll get the pooled proportion times the opposite of the pooled proportion over the first sample size plus the pooled proportion and 1 minus the pooled proportion over the second sample size. You add those together, take the square root. They make this formula, in my opinion, look more complicated when they factor out this piece and make it separate. But we'll discuss that when I do the significance testing video for proportions. So let's jump right into confidence intervals where we will be worried about these two formulas specifically. Also, actually, I should say they do give you some inference formulas on this. Where is the one that I'm looking for? Here it is, right here. Okay. For a confidence interval, you're going to have some statistic or point estimate plus or minus a critical value times the standard error. So they just give you the very generic formula. Okay. They also give you one for the generic test statistic, but we'll talk about that when I do the hypothesis testing video. All right. So enough of that. Let's get into a question. This says each person in a random sample of 1,026 adults in the United States was asked the following question. Based on what you know about the Social Security system today, what would you like Congress and the president to do during the next year? And the response choices and their percentages are shown below. So completely overhaul the system, 19%. Make some major changes, 39%. Make some minor adjustments, 30%. Leave the system the way it is, okay, 11%, and no opinion, 1%. Find a 95% confidence interval for the proportion of all U.S. adults who would respond, make some major changes. So that's this category right here. make some major changes to who would respond make some major changes to this question. Give an interpretation of the confidence interval and give an interpretation of the confidence level. No problem. We can do all of those things. All right. Before we do any of this, and perhaps maybe I should do this, or at least give myself another blank page in case we run out of room. Okay. First thing I should do, okay, is I have to say what I'm doing. We took one sample, and I'm trying to estimate the proportion of adults in the whole country who feel like this. They would make some major changes to the Social Security system. Okay, so that is a 1 prop Z interval. Okay, that is what we are going to be doing here today, a 1 prop Z interval. To start our 1 prop Z interval, we should define the parameter that we're trying to estimate. We are trying to estimate P, the true proportion of adults who would respond, make some major changes to the system to this question. That's what I'm trying to estimate. This is the breakdown only for these 1,026 adults. I want to know the true population proportion, or the true proportion of everybody in the country who feels this way. Okay? Who feels like they want to make some major changes. So should I type that? Can I type that? Let's see. P. I want P to equal the true proportion of U.S. adults who would respond, make some major changes to the survey question. Okay, that is what we are trying to estimate, the true proportion of adults who would respond this way when they were asked this question. Okay. In order to make this confidence interval, though, we have to check our conditions. Okay, condition 1, was the sample random? Random. Does it say it in the question? Random sample, right? So you would say stated. I'm not going to write it because I stink at writing with the mouse, and I'm trying to avoid it whenever I can. Number 2, we're going to build this we're going to build this confidence interval based off of a sampling distribution. We are going to pull a critical value from a sampling distribution. Okay, and the sampling distribution that we're going to use is going to be a normal distribution of z-scores, and we can only use that distribution if we know the sampling distribution of p hat is going to be normally shaped, and that's when we meet the law of large counts. Okay, so since we don't have p, we're going to use p hat to check off these conditions. So I have a sample size of 1,026 adults. And, this sample size is huge. So 39% of 1,026 adults is going to be much bigger than 10. Okay, and then same thing, 1,026 adults times 1 minus p, which if p is 39%, then 1 minus p has to be 61% or 0.61. And again, the sample size is so big that we know that these are going to be way bigger than 10. So check and check. And then my third condition needs to be that we need to make sure we sampled less than 10% of the population. So we're going to say that 1,026 U.S. adults is definitely less than 10% of the population of U.S. adults. Check, check, check. Okay? So we checked our conditions. We defined the parameter that we're trying to estimate. We stated our procedure. Okay? So from here, it's actually pretty easy, right? Remember, the formula is going to be sum point estimate plus or minus some critical value times the standard error from the sampling distribution, where we're going to pull this critical value from. Okay, in this case, my point estimate is going to be p hat, or my sample proportion, plus or minus the critical value. Well, where are we going to get the critical value? They tell us they want, what do we want? A 95% confidence interval. So I need to know what is the critical value going to be for any normal distribution. How many standard deviations, or in this case, since we're going to be using a sampling distribution, how many standard errors do I need to add and subtract to my point estimate to get me a 95% level of confidence? So again, that's an inverse norm question. We should know by now that it's going to come out to be 1.96. But if I hit second distribution, come on now, there it is, and I go down to inverse norm, and I want the 95% area to be in the middle, we should know by now that the area to the left that I can put in here, right? If I got 95 out of the middle, that leaves 2.5 in each tail. So I can either say the area to the left is 0.025, and that will give me the lower critical value on the distribution. Or I could take that 0.25 in the tail and add it to the 0.95 in the middle and say, give me the cutoff for the area to the left being 0.975. And when I hit paste, there's our 1.959. So that's your 1.96, okay, on this distribution. So let's go ahead and fill that part in right now. There's my critical value, why not just carry it out? 1.959, okay, just to be a little more accurate. All right, so we substituted that in, okay. We know p hat already, right? We just got to go back and look. It's 39%. So in our sample, we're saying this is going to be our starting point. Our sample came back with a sample proportion of 39%. So from this 39%, I'm going to add and subtract almost 2 standard errors, but not quite 2 standard errors, a little below. And now we just need to figure out, well, what is the standard error of this sampling distribution of p hats? Okay. Let's go back a page. That standard error is going to be right here. P hat times 1 minus p hat over n. Then take the square root. So for us, for our sake, right, to get this standard error piece, that's going to be the square root of p hat was 39 times 1 minus p hat is 0.61. All over my sample size, which was 1,029. I'll go back and check. 1,026. Ugh. I have to fix that. 1,026. Okay. So let me plug this into my calculator. Second square root. And I want 0.39 times 0.61 divided by 1,026. And the standard error is 0.0152. I'll take it out to 4 decimals. 0.0152. Okay, and then at this point, I'm going to stop doing math, okay? Because my calculator will calculate the interval for me if I just tell it all the information from the problem. How do I get my calculator to do this for me? I'm going to hit Stat. I'm going to scroll over to Tests. And I'm taking a one proportion interval here, right? So I want one prop Z interval. Here's one prop Z test. Nope. Here's two prop Z test. Nope. I want one prop Z interval. There it is, function A. And so one prop Z interval. My confidence level is 95. That's great. All right. My sample size was 1026. And they want me to say X. Okay. They want me to put in the starting point. My starting point was 39%. But how many people then would that be out of 1026? Because this says X, not P hat. So I got to think, all right, well, how many people, right? How many people out of this 1026? So let's see. That's a shame that I have to do this. Can I do 39% times 1026, right? That's my starting point, right? 39%, or if they want a count of the number of people who voted this way, 39% times 1026 seems to be 400.14. Now when I go down to calculate, come on, stat calc. What did I do? No, tests. Sorry, I want a one prop Z interval. Don't know what I did wrong right now. Stop. Please stop. I don't know why it does this to me. All right, one prop Z interval. Let's try this again. Okay. All right, maybe they don't accept decimals in here as a count. So what if I just put in 400? Would that fix the problem? Although that's not really what I want, because now I'm not fully accurate. Okay, so it does give it to me now. So let's just see, look how they calculated P hat is 0.389. That's not the 0.39 that I actually want to start with. So I guess for a particular question like this, you could actually do the math by hand if you want to be super accurate, okay? Because 39% of 1026 turned out to be a decimal, right? So, I mean, I guess if you put this answer down, you'd be pretty darn close. But let's just do it out by hand. So let's figure out what my margin of error is going to be. 1.959 times 0.0152. 1 1 point, I even do no 0.0152 times 1.959. 1.959 times 0.0512. Here's my margin of error. Okay. And now I need to add this to 0.39, and that will give me my upper boundary of my interval. And then I need to subtract this from 0.39. Did I do something wrong? 1.959, 1.959, 0.0152, not 0.0512. Duh. 1.959, I used the wrong number, times 0.0152. That's the right number. Don't make a mistake like that on the exam, all right? So there's my margin of error. That looks better. Now to get the upper boundary, I'll add that to my 0.39 starting point. There's the upper side of my interval. The lower side of my interval is going to be when I take that 39% and I subtract that margin of error. So out to we'll do 4 decimal places. 0.4198. I'll say the upper side of our interval is 0.4198. And the bottom of my interval was 0.3602, 0.3602. There's your interval. Let's see just how close the calculator did actually get us when I did stat tests. Let's find I have to hit this arrow key button slow because sometimes this thing just goes rogue. One prop Z interval, and as I calculated again using 400 as the count, what did they get? 0.36002 to 0.41971. I got 0.3602 to 0.4198. So we're pretty darn close out to, 4 decimal places. We're pretty close here. So for this one, I just decided to calculate it by hand because when the calculator wants to run a one prop Z interval, it wants you to give a count of the number of people who voted this way divided by the sample size, and it calculates p hat on its own. But since 39% of 1,026 people ended up being a decimal, I just decided to do this by hand so I didn't have to mess around with the calculator. Okay? Then they also want us to interpret. What do they want us to do? Interpret the confidence interval. It's always the same interpretation. We are 95% confident that the interval from 0.3602 to 0.4198 will contain whatever it is we were trying to estimate, in this case, the true proportion of U.S. adults who would respond, make some major changes to the survey question. If they ask you to interpret the confidence level, a confidence level of 95% says that 95% of the intervals calculated using this procedure will contain the parameter we are trying to estimate. Okay, so that tells you right away, right? If you're making a 95% confidence interval, 5% of the time your interval is actually going to miss, and it is not going to contain the true population proportion, but 95% of the time it will. Okay, and then what is this B question down here? That's not really the point of my video here, but what does it say? An advocate for leaving the system as it is now, so that would be one of these people, one of these 11%, commented, based on this poll, only 39% of all adults in the sample responded that they want some major changes made to the system, while 41% responded that they want only minor changes or no changes at all. So I guess they added these two probabilities together. Therefore, we should not change the system. Explain why this statement, while technically correct, is misleading. Well, it's misleading because you leave out this 19% of people who want to completely overhaul the system, right? So this part doesn't really have anything to do with confidence intervals, but this person is saying this is a person who doesn't really want to change the system, right? What did they say? An advocate for leaving the system alone. He says, all right, well, the people who want minor adjustments plus the people who want to leave the system alone completely adds up to 41%. That's greater than the percentage of people who want to make major changes. So since the amount of people who want to make minor changes or no changes at all is greater than the percentage of people who want to make major changes, then we shouldn't change the system. But he conveniently left out that 19% of people want to completely overhaul the system. So that, I guess, is even more extreme than just making major changes. So him using these 41% of people to justify not making any changes doesn't really add up, because even though only 39% of people want to make major changes, there's another 19% who want to completely throw this thing out and start over. All right. So that's just a little bit of an interpretation question. All right. Let's wrap this thing up with a 2-prop Z interval. Okay. This one says a large company has two shifts, a day shift and a night shift. Parts produced by the two shifts must meet the same specifications. The manager of the company believes that there is a difference in the proportion of parts produced within specifications by the two shifts. To investigate this belief, random samples of parts that were produced on each of these shifts were selected. For day shift, it was 188 out of 200 parts. And for night shift, it was 180 out of 200 parts. Find a 96% confidence interval to estimate the difference in proportions for the parts produced within specifications by the two shifts. So first, let's just spell some things out here, right? You guys would have to state your procedure. All right, this procedure is going to be a two prop Z interval. All right. And then you would have to define your parameter. And our parameter is going to be, let's call it P hat, because I'm typing here. So P hat day shift minus P hat night shift, which is going to be equal to the true difference in the proportion of parts that meet specifications between the day shift and the night shift. Okay, so I'll pull this out and move it down, right? So they want, what does it say here? To estimate the difference in proportions of the parts produced within the two shifts. And they give us the day shift information first, and then they give us the night shift. So I'm going to take this we're going to do day shift minus night shift. So P hat from the daytime minus P hat from the night. Actually, that was stupid. I made a mistake. Hopefully you guys caught it. I'm defining my parameter. I should not be speaking in terms of P hats. Okay. I'm trying to estimate the true difference. So I'm talking about P day. So that's the proportion of parts that meet specifications on the day shift minus P night. Okay. The true proportion. So I said P hat, which is sample proportions. That's going to be our point estimate. But when you're defining the parameter, always speak in terms of the population parameter. Okay. Now let's just assume that all the conditions have been met, right? Random sample check. These 200 parts from the day and night shift are less than 10% of all the parts produced on the day and night shift. Let's say check. And let's say large counts has been met for both of these samples, right? 88 out of 200 and then one. So that would give you your P hat, right? So if we have 88 parts that met specifications, that means we had 12 parts that didn't. Here we had 180 parts that met specifications. That means we had 20 parts that didn't. All those numbers are bigger than 10. So the large counts condition is going to be met for both of these individual sampling distributions. All right. So let's just make one more thing here, right? To figure out what formula we're going to need. Okay. We know we need some point estimate again, right? Plus or minus some critical value times the standard error of the combined distribution this time. Okay, my point estimate is going to be P hat from the day shift, or the proportion of my sample from the day shift that met specifications, minus P hat for the night shift. Okay, plus or minus that critical value, which is going to be that Z, that special Z star number, times the square root. And now we're dealing with two different samples. So we're going to do P hat for the day shift times 1 minus P hat for the day shift over the sample size for the day shift, which we already happen to know is 200. And to that, we have to add, remember, even though we're subtracting the proportions, the combined sampling distribution is going to have more variation. Okay, so these variances always add in here. So to this, we're going to add p hat for the night shift times 1 minus p hat for the night shift all over 200. Okay. So now we just got to plug things in here, right, to show our work. So we got to figure out our p hats. On the day shift, we were 188 out of 200. So clear this out. 188. Shoot. 188 out of 200. So in day shift, we're at 94%. It looks like the night shift is going to be 90%, or 180 out of 200 is 90%. So the sample difference is going to be about 4 percentage points, right? So I'll write that in here, right? P hat day shift, 0.94 minus P hat for the night shift, 0.90. Plus or minus, they want the critical value for a 96% confidence interval. All right, that's again inverse norm. And if I'm dealing with the middle 96 and I want either one of these, this is a negative z-score, this is a positive z-score. If I'm dealing with 0.96 in the middle, that leaves 4% for the tails. That's 2% in this tail, or 2% in this tail. So to find my critical value, okay, I can either say, give me the cutoff for 2% to the left, or for 98% to the left, 96 and 2 in the tail. So again, that's going to be an inverse norm thing, second distribution, inverse norm. Okay, we're going to make the area to the left 98. And now our critical value is going to be 2.0537. I'll round that off to 2.054. All right, 2.054. All right, times the square root. Okay, this is going to be a whole mess, but no problem. P hat for the daytime was 94%, so 0.94 times 1 minus that, which would be 6%, or 0.06, all over the 200 pieces that I sampled, plus, all right, P hat from the night shift was 90, or 0.90, all right, times 1 minus that, which is going to be 0.10, all over 200. All right, and that's the work. You showed all the work. And now this one you could definitely do in the calculator because they gave us counts. Okay, we calculated p hat on our own. So you'll see what I'm talking about. The reason I didn't use the calculator to generate the interval over here is because we didn't know, or we did know, 39% of 1,026 people gave me a decimal, right? So I didn't want to, my calculator didn't accept a decimal as the input for the count of how many people voted that they wanted to make major changes, right? So I couldn't do that decimal, so I had to change it to 400. So then my p hat was slightly different than what the question gave me. It was like 0.38 and change. Okay, so I calculated this one manually without the calculator. But this one, we calculated the p hats manually. They didn't just give them to us. They said 188 out of 200 on the day shift and 180 out of 200 on the night shift. It's unfortunate that the calculator only accepts counts and not proportions. But now when I go to stat tests and I go to my 2-prop z interval, don't pick 2 sample z interval. That's going to use the wrong critical values. You want 2-prop z interval. And look, Here you go, right? It's taking everything as account. We had 188 parts, meet specifications. How come nothing is happening when I type? 188 out of 200 parts met specifications in day shift. I'll make the second one night shift because we did day shift minus night shift. So day shift is X1N1. Night shift is going to be the 180 out of 200. Okay, and that's really all the calculator needs. The calculator wants, I think, a 96% interval here. And I'll hit calculate. And there it is, right? Here are your p-hats, right? P-hat 1, 94, p-hat 2, 90. We said that. They're giving an interval for the true mean difference to be somewhere between negative 0.01 and positive 0.09. There is a 0 in this interval. That means something. That means that we do not have sufficient evidence that the day shift is better than the night shift. If this was a hypothesis test, they're not asking us to run a hypothesis test right now, but if they're just asked, do you have significant evidence to say that day shift is pumping out parts at a better rate than night shift? The answer is no, because our confidence interval for the true difference between the two shifts contains a 0, which means it's possible, in fact, plausible, that there's actually no difference between the day shift and the night shift. And on the day that we took these samples, day shift just had a slightly better time than night shift. Okay? Is that all they asked us to do for this question, was make the interval? No, it says, based on this confidence interval, do you think the difference in the proportion of parts produced within specifications by the two shifts is significantly different from 0? We just answered that, right? We just answered that question. No, my interval has a 0 in it. So I do not have significant evidence to tell me that there is some sort of difference between the quality of these two shifts, because my 96% confidence interval contains a 0. Alrighty? So that's it. That's confidence intervals. 1 prop Z interval and 2 prop Z interval. Happy studying.